Hey everybody, so today we're going to talk about rational and irrational numbers, what the difference is, okay? So let's start out with real numbers. All real numbers. And do you remember the sign for all real numbers? It's going to look like that, okay? Sometimes just all real numbers, okay? So, let's split the real numbers into two categories. Now, there's more than two categories, but for today we'll only focus on two. And that is rational numbers and irrationals. Okay? Alright, so for all intents and purposes, we'll start with the rational numbers and look at these. Okay? Alright. So let's look at the signs for each. For a rational number, it's a Q. You remember what we said? Why it's a Q? We'll talk about that in just a little bit. So the opposite of rational is irrational. So it would be just a Q with a bar over it or a line over it, meaning not rational. Sometimes you would hear it called Q bar or bar Q. I call it food bar, so anyway, so let's take a look at why it's a Q. And I forgot my eraser. Got to be prepared. Alright, so let's erase this. What is a Q? If you said that it was a quotient, you were right. Q stands for quotient. And what is a quotient? Well, it's simply a fraction. That basically says 2 can be divided by 3. Okay? So anytime there is a rational number, it's going to be depicted as a fraction or a decimal that has a definite ending. Okay? All right, let's take a look at some examples. Okay, of rational numbers. Well, what about 2? It's most certainly rational because it can be also a fraction. Remember, any whole number over 1 is itself. So 2 over 1 is 2. That's a rational number. What about 0.5? Okay, well that's 5 over 10, which is a fraction, and we know what equals a half, 1/2. All of these are rational numbers. What about 0.7 repeater? Now remember, when the line is over the number, really, that's like saying, and it goes on forever and forever and forever. So instead of just going 0.77777, we just eliminate this part right here, and we just draw a line over it. Now, it's still rational, okay? Because if we turn this into a fraction, it would be 7 over 9. All right, you try to do one. 2.6. Is 2.6 rational or irrational? Okay. Well, let's turn it into a decimal, which would be 2 and 6 over 10ths equals 2 3/5. I had to reduce that. So is this rational? Yes, it is, because it's definite. It has a definite ending. Okay. What about 0.135296? Is that rational? Well, do the rational test. That's what I call it. So, if I turn it into a fraction, $13,529 over 100,000, that's definite. It ends. It doesn't continue. It's rational. Okay? All right, let's look at irrational numbers now. The most famous irrational number is pi, which equals 3.14 da 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 da. It goes on and on and on. It's actually large as far as decimals is concerned. There's no repeating patterns. There's no end. It just keeps going. Now, you may have heard that you can put it as a decimal, 22 over 7. Well, that is just an approximation. That is not exactly, because this ends, I think that this is 3.1428, and it ends. Irrational numbers never, ever, ever, ever end. Okay? Now, let's talk about repeaters for a minute. 0.79 repeater. Okay? So, this is what this looks like. Both numbers, there's a line over both numbers. So that literally means 0.79, 79, 79, 79, and it just keeps going forever. 79, 79, 79. That is a rational number because it's a repeating decimal. Okay? And you can also turn this into a fraction of 79 over 99. You wonder how I got that? I'll show that in a future video. Okay? So, you may be saying to yourself, well, Thomas, you've showed us a lot of more examples of rational numbers than you have irrational. There must be more rationals. Well, that's not true by a long shot. If I was to put all real numbers into a lottery, every number imaginable, okay? And then I randomly had a button that I pushed and it randomly shot out a number. There is a 100% chance that I would get an irrational number. That's how many more irrational numbers than there are rational numbers. Now, we mostly, when you take the test, will be dealing with rational numbers. Why? Because, well, that's what we count. That's just what we do. We look at the rational numbers, all real numbers. So, keep in mind that irrationals do not repeat. They keep going on and on and on. Another thing about an irrational is you can never convert it into a decimal. Never ever turn it into a fraction. A rational number will not be a fraction. It will only be a decimal. Okay? So if we're going to be normally working with rationals, then what are the irrationals to look for? Well, most of the time they're going to be when you're dealing with square roots or cube roots. Okay? So square root of 2 is ugly, 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 ugly. It's the irrational. Okay? It's a decimal that keeps going on and on and on. What about the square root of 4? Well, we know that the answer is 2. And we know 2 is rational. So if it's a perfect square, then it's rational because we know that 2 can be turned into a fraction 2 over 1. Okay? What about the cube root? Remember when we do a cube root, we put a little 3 in there. The cube root of 8. Well, if you have any experience with this, go back and check my videos on square roots and cube roots. If you're unsure, this also equals 2. Okay? And so that would be rational, right? Because same as this, 2 over 1. Now, so, once again, irrationals, you're going to see them in the form of square roots and cube roots if they're not perfect squares or perfect cubes, meaning they don't have a definitive integer number here that can be turned into a fraction. All right, so sum this up. Irrationals. They do not repeat, and they do not terminate. Okay? So, most of irrational numbers come in the form of, say, the square root of 145. Square root of 145 does not repeat, and it does not terminate. But the square root of 144, a rational number, is a perfect square, which we know to be 12. Okay? I'll see you next time in the next video. Make sure you don't be late.